now it's okay.
I'm recording this presentation.
I don't hear you.
I'm recording this presentation.
Okay, sure. Thank you so much. Okay, so let's see it. I cannot see my screen. Okay. All right, so thank you everybody for coming to this talk. Especially I want to introduce about our current effort in my research lab. Especially we are doing AI-empowered robotics and building of some robotic system. Consider about the hardware issue versus the software issue together with AI solution. And then now we want to nearly bring some power of the quantum computing to this AI empowered robotics research. So that's why I said that quantum is good for the optimization, but can you build some intelligence with the quantum for the robotics? That's the my topic. And especially I want to bring out the trustworthy issue. It's very important in the robotics domain. So let's see. I can mute somebody's talk. Okay, so it's better now. Yeah, sorry for that. Okay, so the important topic we want to do is the AI-empowered robotics. And we want to build some trustworthy robotics. That's our goal. And we want to use some quantum computing for the intelligence. So that is the one. I'm going to start the presentation and look, we'll continue with some portion of the this presentation based on our research during the summer. Okay, so I want to introduce the first one is the digital twin technologies. It's introduced by the NASA around 2000, early 2000. They use this digital twin concept for some airspace and the space environment. They try to building of the digital twin, monitoring of the spacecraft over the spaces, and then especially see whether can we do the monitoring of the activity and then real-time inspection about the situation of the spacecraft. So this is continuously building in then 2010, 2015. But once you're coming to the 2020, I think you see that the remote operation is possible, and then we can do real-time performance evaluation, and then you can control about some of the environment with some of the devices. Can be a robot, it can be a non-robot necessary, but this concept become popular now. It's not only about the space environment research, but manufacturing system. They use some digital twin to building about the twin for the digital twin versus the real twin, and they're working together to conducting of some job. And especially they start to apply this concept to the full life cycle of the management of some design of some application or training of this machine or robot, and then do the monitoring and then try to find out are there any obstacle or some of the major behavior which is we can handle without much of the manual handling, but it can be automated. But I think a major problem is the environment, dynamic environment is keep changing, and we have so many data coming from different sources, and how much you understand about the data and when to use and how to use is the matter. So because of that, we need some of the good designing of digital twin to apply to the particular domain. So in from this angle, AI empowered robotics people try to see some data-driven approach for the robotics. Previously, a lot of people coming from mechanical engineering and the electrical engineering, they building of the robot for the static robot. But now AI is coming to the robot. They said that, can I do the automation? Consider about some data coming from the environment, data coming from maybe robot itself, or it can be coming from the human, because robots doing for the human, not only for the robot to the robot collaboration aspect. So here we have some room for the AI and machine learning, enhance about some understanding and operation in the deep space. So once you're coming to the robotics domain, I think the main concept is the digital twin is the twin between the real robot versus the AI robot. They are working together. It's not just one directional. If you see the diagram, show the real robot to the AI robot, right? But the AI robot is actually helping the real robot. The motivation force to think about this collaboration is the real robot has a very limited computing power, and then even the GPU is very limited. So we are not able to deploy some deep learning model to the real robot. And AI robot has not much idea about the environment and then some changing happening in the particular situation. So we don't have much sensing ability from the AI robot. So we need some collaboration between real robot because real robot has some sensing capability. AI robot has some intelligence, right? So based on this collaboration, we're able to do the much better job in the some new task or new environment. Because the known environment, we can build some static model to handling of the operation. But the new environment, new task, we have to teach the robot how to do it, right? So many unexpected situations happening in the real world situation. From that angle, I think a digital twin for the robot, we have some advantage like real-time mirroring of the virtual versus the real, and because we understand about what's going on through the real robot sensing, right? And then another part is we're able to understand about the predictive control. That means not only about what you know, but if something new is coming, we should be able to reasoning and then try to handling of some obstacles or some unexpected situations. So predictive control is required. Another is we may need some of the intelligence, not necessarily every intelligence in the AI side, but some intelligence may be available in the real robot. So how do you distribute some of the intelligence between the real robot versus AI robot, right? So that is the kind of problem. Another part is a collaboration. How do you build some robot collaboration? It can be a real robot between the real robot to real robot, or it can be between the real robot with the AI robot. But we need some collaboration. The, the the modeling is required because the first one is the who is doing what, and and how do you communicate each other, and how do you make a decision based on the different opinion coming from different the agent, which is robot, right? From that angle, we have a lot of interaction going on, and then a lot of job is required, and good modeling is required to do the collaboration between the real robot versus AI robot. And especially, we are very, very interesting about how do you trust robot operation and how safe they are. Because we have a robot doing humanoid robot, they're helping for the people carrying out the maybe pet in the house. But how do you trust AI operation? Whether it's the trust is the matter, and then we should be able to understand about their behavior, and then able to figuring out I can really trust the robot to take care of my family or my baby or my elderly people. So that is the thing. So if you see the some research going on in this robotics domain, people try to talk about the digital twin for the robotics and try to see, can I do the mirroring of these two robots, like a real robot versus the physical robot versus the AI robot, and then we need some of the reasoning capability. To do this one, assumption is that we may get some lot of data coming from physical twin, which is the sound and vision and the radar and the speed and the pressure sensor, and then we have a more sensing ability is there for the robot, which is physical twin. And second one is that we need some good data sharing, and then we have the good understanding about what's going on between the physical twin versus virtual twin. So we need some good sharing knowledge between the two different twin, physical versus virtual. And virtual twin, we cannot see, right? Because of that, we are able to representing of the virtual twin in a certain manner. So visual representation is required for the virtual twin. I think interesting part from the virtual twin is the AI twin, which has a good ability to understand about some task and the sequence of task, and then handling of some task, and then understand about some decision, what to do in urgency versus regular activity may be different, and then finding of some object and manipulate of the object, right? So there are a lot of reasoning capability required from the virtual twin. And then between that, we need some strategy. We have a multiple decision coming. How about this a good decision to make some good action? And that can be a regular activity, it can be urgent situation. But urgent situation, we need a real-time response, right? So because of that, decision should be a more scalable and then reliable and then efficient. So that is a consideration. And then actual action can be done by the physical twin. So I think this one diagram shows very nicely what's going on between the physical twin versus the virtual twin to conducting of the some job. So I will keep moving. And what's going on in the robotics research? You see that we see there's some lot of progress from the multiple researcher, people looking from the data in the visual data versus audio data, even the touch data, right? And then based on that, they do the sum of the activity. I think if you see the A diagram, they show that this is the first person view and bird eye view for the some environment perception, because perception is the some environment is very complicated. Like it can be apartment, it can be a maybe big house, or it can be a maybe public site, right? And then we have a lot of different space and the room and different activity going on. And then not only the space, but here we have a lot of objects associated with particular room, like a bathroom and living room, kitchen. They are different objects, right? So try to understand where you are and what kind of activity are you doing. To do this one, definitely we have to understand about the environmental perception. Second part, I think is interesting one is that they are adding of the some of the image together with the audio data to understand about some the audio activity and then represent in the space. Third one is building of the some embodied sensor. That means the scanning is available particular one. They understand about what's happening in the particular object based on their embedded scanning technology. Continue to this AI robotics side. I think the A diagram show that how do you handling of the activity in safe and then collision without any collision and then do the navigation. So we have a pretty famous problem is called the object goal navigation. That means that they are looking for the particular object in the different room, but you have to go through the workable spaces and without any collision and the finding of the object, because there are many rooms, there are many partition, and then sometimes we cannot see the object, but we have to find some object. So people try to come up with a good algorithm how to navigate the environment to find some object. Right? So that is important, especially safe and then collision avoidance is the important problem there. And some people working on the robot arm and how do you manipulate of the sum of the object and then do the some control of the motion to manipulate of the object. And then more than just simple motion, no, we have to make a plan, because the cooking, we need a planning for the cooking. First step, second step, third step, and how the robot arm is doing to conducting all this. And then last diagram, they show that how do you use some deep learning model like a transformer, right? And then try to really represent about the visual input through the multi-step autonomous task. So that means the task become more complicated and the location of the task is actually changing from time to time. And this robot can be navigating and doing some action, so the problem become more complicated. So this is the one. And then if you continue working on that, I think recently a lot of research going on using large language model to interpret about some real world situation and then determine about the object and then make a decision and then try to explain about why I'm doing this one and then what's happening and then what's the best action I have to do. So we see that a lot of interesting scenario, taking care of the house versus taking care of people and then conducting of the job. And then I think to understand this one, we have to understand about the environment. That's a key point. And then see whether this is the proper way to do it, or this is are there any risk to handling of this part. So if you see the C, actually this is pretty advanced model because they try to do the navigation decision using of the knowledge graph. Knowledge graph is the symbolic AI. People try to representing of the environment based on the graph, which is the knowledge graph is the modern graph. So we are able to building of the knowledge graph based on the object relationship or object with a value can be represented. So knowledge graph actually giving us a good idea to summarizing of the environment and activity and the status can be detecting, and then based on that we can make a good decision. This is the latest research going on in the knowledge graph with the deep learning. We call the neuro-symbolic AI technology. It's used for the robotics. Okay, so I want to introduce our current effort for the robotics, AI empowered robotics. This work is done by my PhD students and my former PhD students, which is the Dr. Ho. And let me show the video.
Okay, so the first task is put the pound cake on the bookshelf, and you can see that we walk toward the bookshelf and place the pancake on the top. Now we put the clothes inside the kitchen cabinet. As you can see, we walk toward the kitchen, and then we place the clothes inside the cabinet. Successful. Okay, the third task is to put the book on the bookshelf. You can see that similar to the pound cake on the top. Now, this task is unsuccessful because it's an impractical task. The model got confused a little bit. Here, the garbage can is not supported by the simulation environment, therefore it was not successful. Here comes the object manipulation task. So the first task is to place the ball inside the kitchen cabinet. You can see that we generate a series of instructions, and then we use the 3D grid to move the robot arm around. Okay, and then we place it inside the cabinet. The next task is to put the paper plate in the sink. And you can see that we move our uh, robot arm towards the sink using the 3D grid. Okay, after that, we drop the plate onto the sink.
Okay, so this demonstration actually to show the collaboration between the real robot versus virtual robot based on the digital twin we design. I think some of the interesting innovation we made for this research is that can you nearly use the knowledge graph as some of the backbone to make a better decision about the task sequence of task and then location and then object manipulation. So knowledge graph based planning, and then we're gonna use some latest technology like a large language model. We use the T5 model for the embedding of this. The GNN encoder is the T5 based encoder, and we connect that to the transformer. So we teach the transformer what's a typical active sequence of action I have to do to handle about the particular task. And based on the transform-based motion, the prediction, we're able to generate some of the sequence of action, and we're able to handling of the task without much problem. So here is the digital twin safety layer is the built based on the latest technology. And another good thing about is that we are sharing of the 2D grid and then 3D grid. You see that 3D grid view in here. That means we're able to representing of each object in terms X, Y, Z, and even the robot arm position can be represented as X, Y, Z, and then try to teach robot how to move this one and how to handle this job and what's the next thing you have to do, where to find the object, so on and so forth can be guide them through our uh, neuro-symbolic technology. So this is one. And then currently we achieved the state-of research because we're able to attain the almost 100% of executable rate, but success rate is a bit lower, like a 64.6, but still better than state-of research. The reason of this success rate is not high. The reason is, for example, one of the task grab the object can in the real virtual home environment, but this home environment does not supporting about the object like object grabbing object for this particular thing. So because of that, we have some failure, but this is not the actual failure. This is not observable by the simulation environment. But our our achievement is not only simulation, but we're able to connect the real robot with the simulate robot. So simulate robot from this video, virtual home, humanoid avatar. But we're able to connect to the chatbot, which is real robot. And real robot is actually doing conducting of the job, which is the virtual robot is doing. Like what we are seeing from video, we have a virtual robot arm showing together with the real robot, right? So this is what we are doing. And then
Okay, so the first task is
I want to really bring that why we need a quantum for the robotics. First problem is the classical robotic solution is limited because the environment is so complex. And then if you are doing multiple robot situation, I just showed that one robot situation, but if you have multiple robot situation, scheduling and then conducting of the job is the MP hard problem. And scalability is the major issue, may not have real time. Right, and then to do this one, probably we may need some help from the quantum. Another is the heuristic method is not working because the dynamic environment and then huge uncertainty situations, so obstacle and then changing condition, and then maybe we cannot find object. We cannot do this one because of something happening in that environment. So from that angle, heuristic method is not working. That's why learning based approach is the working, but still it's limited because our knowledge graph may not be comprehensive to understand about the environment. In that case, some task cannot handle that properly. Next one is the perception and reasoning. This is a pretty complex problem. So it's not easy to handling about the particular task dealing with multiple objects, and the object is in different location, and order of the task is the different, and action may be different way, right? So from there and go, very complex problem, and the real-time new planning is one of the hardest problem we can think. So from large environment and the multiple robot probably is not good based on what we developed so far. And another big problem is the how do you determine evaluating about robot behavior, right? And then how much trust you can put to the particular robot activity. So can you do the some of the measurement of trust, and then we also can have a distribute decision making process, not by the one intelligence. We need to distribute intelligence among the multiple robot, and then robot collaboration can really provide some of the good idea how good they are and then how trusty it is. So classical optimal solution may not be good enough, right? Because of that, quantum can give up to a certain level, but we need more than what quantum can provide us. Right. So from that angle, I think this can be a win-win situation from AI side versus quantum side, but we need a good connection between them. So far what we said is we're able to build a digital twin between the real robot versus the AI robot. We're able to show some of the task in the particular scenario, but major issue was the real-time issue, communication between AI robot versus a real robot. And we may need a more powerful predictive ability to give us some feedback from real to the AI to the real. And then we may need some help from the quantum. So from the quantum enhancement, I think we can think about several different one. Superposition, I think spelling mistake there, superposition, especially we try to find out some possibility, and then how many possible situation we can think, and then to simulate that, right? So we're able to use the superposition technology to see, and then entanglement, I think we can understand about the state. So it's not just the one agent, multi-agent, the state can be coordinated in evaluating. And we also have very good quantum work and the kernel function available, so we can build some of the global reasoning on the graph. It can be scalable, right? And then quantum annealing is something we can do that in the scaling under the constraint. And then we can think about some energy function or some dynamic way to determine how do you handling of some task with the minimum cost and the maximum outcome, and minimum cost and maximum reward. So I think some concept from the reinforcement learning can be very nicely connect to the quantum. So, okay, so why now? Right. So I think most of you are familiar with the Qiskit, and quantum simulation is available, and this is great way to connecting classical computing with the quantum computing in the pipeline. So we said that maybe deep learning and then AI is classical computing, but we need help from the quantum, even the beginning, not necessarily in the final stage. So pipeline, maybe we try to find out the way we need the quantum, and then we're able to put them together as the pipeline, and then try to achieve some goal. Second one is we have a very good workflow for the robotics, like scheduling, navigation, and thrust measurement, and the handling of some uncertain situation. But it can be nicely connect to the quantum formulation, especially Cubo, and then quantum work, and then components available. And some of the research, they show that scalability is increased significantly. So scale root of the n or exponential speed up for the searching and matching and the scheduling task. Once we represent some our environment as a kind of the abstract level like a graph. So point is the quantum computing is not a replacement of the classical robotics, but this can be an augmentation it with some new paradigm, especially how do you apply to the real-time optimization and reasoning, and then how to evaluate the trust in the complex and adaptive system. So I want to bring our research during the summer. Luke actually do some scheduling problem using quantum approach. So I think we will talk more detail, but I will try to give it some high level. We try to do the real-time coordination, consider about the multi-level scheduling problem, which is the NP hard problem. But also classical heuristic is not working fine in some of the situation like a fault, delay, or any configuration side. So he come up with some of the Cubo metrics and then try to apply some quantum annealing technology to minimize the delay and conflict penalty. And then we have also achieved the real-time replanning during the mission changing. So he will give you some detail. So Luke, can you please go ahead?
Yes. What we were trying to take a look at is we have multiple different robots with different capabilities who are trying to be assigned a set of tasks. Now there's some very basic constraints here that we can't assign more than one task to one robot at one time. But then also whenever you consider things like different capabilities, that this robot can do this task but this one can't, these tasks take different amount of time, and that they have different priorities. And so it's a non-trivial thing, even with a relatively small number of tasks, to optimally or even successfully schedule all of these tasks for these things. Task scheduling is one of those things that we seem to deal with in our everyday life that we have no idea of how truly complex it is. You start getting into these factorial type combinations. So what we did was that we represent our tasks as a directed acyclic graph. This is a graph that kind of looks like a tree, and that the edges are one directional. You can only go from one task to another. So what this does is that oftentimes that if I am going to make a bowl of cereal, I have to get the bowl before I pour the milk. That's that precedence that's so important in these tasks. And so what I was able to do was I was representing these tasks with a directed acyclic graph. And these are generic in their instance, but they have real-world application. Now each task took between 1 time unit to 8 time units, and they have different priorities that, extinguishing the fire has a higher priority than mopping the floor, whatever the case is. But, these tasks have their own priority. And so what we did then was encoded these into that Cubo matrix, like I was talking about this morning, where I have this large matrix where each task can occur in a certain slot. And then what we try to do is use this Cubo plus QA-OA and solved it with simulated annealing on a D-Wave software development kit. So we were able to generate and solve large and realistic matrices like this, showing the feasibility of this. We wanted to show how this method could compare to some of the leading solvers out there, including CPSAT and oftentimes random topological sort. As we're talking about, these state spaces explode so quickly that we run into a thing where oftentimes the methods that we're using to solve them can be nowhere near complete, and is more kind of like a guess and check type of system. we tested this on a range of parameters. We had between 60 and 200 tasks. And as a time constraint, we afforded less time than it would take to complete all the tasks. This is a place where many classical solvers really struggle. It's a little bit easier if you have sufficient time to complete all the tasks, but if you don't have sufficient time to complete all the tasks, you have these differing priorities and you have the precedence. You know, you have to get the bowl out before you pour the milk example I gave. Then that's what really pushes the limits on what these classical schedulers can achieve. In our Cubo, we encoded this penalty and reward with a range of variables that are connected to each other. And so, breaking precedence or giving more than one assignment to one robot at a time had huge penalties, whereas doing things in the least efficient way had penalties. And then we also had penalties for doing things not according to priority. So this is a basic example of a directed acyclic graph. So what we're doing is using this graph to represent the order of operations that have to be done for responding to a hazmat situation. So there's been a major chemical spill, all right? So there's an order that we have to initiate these tasks in, all right? First, we have to initiate robot systems, but you see that there's these very unique precedents that has to happen, that we have to have I happen before both H and P. So these, we might assign two tasks that need, all right, we need to upload sensor data to the base and locate the damage site. Well, then we're going to have to fill in that directed acyclic graph, everything that came before it. Next, Dr. Lee. So we have to, add all these other tasks to that. And so we have to penalize any schedule that doesn't add these systems to that list of priorities and that doesn't accomplish them in the correct order. Now, that's a very basic example I gave. I believe this example is around 150 nodes, and that's not unreasonable. So often we become very accustomed to all the things that we do. But, in your morning commute, you probably had a whole list of tasks like this that included that you've fueled your car, that you're dressed for the weather, that you turn at this intersection, that you do this, and we think of it as these linear things, but especially whenever you have multiple agents coordinating together, you end up with these highly complex directed acyclic graphs. So what we then do is we take these directed acyclic graphs representing all the tasks and how they flow into each other and encode them into that Cubo matrix used in the simulated annealing. We have to take into account the duration of the tasks, that only one agent can do a task at a time, and that also that agent has to be capable of doing the task. Those dependencies, that it's accomplished all the necessary tasks before then, as well as deadlines, that sometimes things are time sensitive, that it's no longer important to extinguish the fire if the house is burnt down. There is a timeline on these things once they're assigned. As well as multi-agent concerns, that you can have multiple robotic agents getting in the way of one another, that you may need to have more than one robot respond to a task if it's complex. And then as well as that priority, that there are some things that are more important to get done than others, especially whenever there's insufficient time to accomplish all of the tasks. So these Cubo matrices, and as a very basic example here, is that the default is basically a zero matrix, but we can add rewards for appropriately assigning a task and provide penalty for over assigning an agent, or assign penalties for breaking that precedence constraint, that hey, task A has to be done before task B. So scheduling task B in time slot 1 and task A in time slot 2 is inappropriate. So with annealing on this cubo, this is a map of this simulated annealing on this energy descent. Earlier I talked about these expectation values that we'll get out of an estimator, and these are the kinds of results that we're getting out of this simulated annealing, where we have an energy value that we're trying to minimize out of our quantum circuit operating on this cubo matrix. So this was my results from these tasks with this, where I applied Cubo plus that simulated annealing plus CP-SAT, which is the leading classical method, and I accumulated far less penalties on these results. As we scale these problems up to where there's hundreds of tasks with complex precedence constraints and priorities, classical methods really struggle because they're at best doing a heuristic guess and check type of methodology. And whereas we're not doing a fully deterministic approach to this, we're still in this NISQ era, and we're trying to balance the capabilities of our quantum computing with the existing hardware. We are able to, by leveraging that superposition and entanglement, get significantly better results on this scheduling.
Okay, thank you. And I want to quickly introduce about two research conducted by the RU during the summer, RU fellow during the summer. So we conduct 10 weeks of training with the undergraduate research experience during the summertime. And students from the California State University, she conducting of some research related to the task allocation, which is somehow related to the look aspect, but she used some quantum optimization technology, especially try to understand about adversarial multi-agent system. So this paper will be presented tomorrow in the ICDM symposium, RU symposium tomorrow. But anyway, what we have done is that we try to introduce about some resilient talk allocation in the multi-lobos team, especially dealing with the disaster response mission. And she come up with a very interesting scenario. For example, we are able to represent about the robot and then task in the graph manner, and then we have very good data set available to see graph foraging problem, which is cyber physical threat, and then relate to the GPS spooling and the fake task and the communication loss. And approach-wise, she used the Cubo formalization about the trust measurement and the urgency distance and the coalition rule. And the solver, she used the NIL, which is the quantum inspired simulation annual. And the defense mechanism, she used the trust decay control and try to do the recovering of the agents and the handling about the urgency based on the penalty. And overall evaluation, she used the two different benchmark. One is the MRTA on 100 real benchmarking data. Another thing is that she synthesized some data representing of some hospital setting and 5 floor and 720 rooms there. And then she injecting of the attack to this graph and see that whether grid approach, which is traditional optimization technique, which is grid UDT versus the MILP, and then compare with the Cubo. Tabo search is the one, and then overall finding is a Cubo nil preserve the final trust 0.91 compared to the traditional optimization grid approach 0.29, and then 24% of the task can be recovered complete, and then 16% of the task can be recovered, which is the spooled agent situation. And baseline is the Cubo versus MILP doing good job about the coordination, but grid approach is not really reliable. So that's one. And then overall finding is I think we can build some good trust solution based on the global Cubo optimizer, and then especially dealing with some attack to some robot system. I think this is a detail about what she discovered, and then overall, if you see the figure 7, this is a good summary about the Cuba Tabo is doing good job in overall and consider about some trust and then recovery versus attack handling situation. we have one more paper is done by the Joseph and then Jaden, and then somehow similar but a bit different because here they try to bring some of the heterogeneous robot and then in the hospital setting again. But this environment is more like a changing environment. So it's not just static environment, and then event can be applied to the particular understand about the situation. They use some Neopoly knowledge graph idea, and then they use some optimization technique to figuring out what is the trust situation in this setting. And then they try to use some some of the traditional the routing algorithm. A star, D star is the pretty famous for the static algorithm to navigate shortest path in the particular one. And then try to compare it's possible to do that in the quantum inspired computing. So real for the Kubo and the Hungarian approach for the snapshot matching they apply. So if you see that this event model, they try to understand about the situation and try to figuring out how do you handle that. In their simulation data, 384 node, 440 edge, and even event triggering optimization can be done by the 1-2 HG. And then in this dynamic environment, what is the possible to figuring out the safety distance, right? So they're adding up the some of the hazard aware the routing situation. And then they introduce an interesting concept like a 12 different robot, eight different sensors. And then how to do the rescue of the people within time, right? And then try to see, can I do the maximization? And then they come up with the Cubo adopt the first underlying task update and Korean Excel the stable snapshot. So overall, I think they show that in this particular situation and changing situation and multiple robot and multiple sensor, how they are working together to rescue people in the dynamic environment. And then this is some result, but they measure that based on the D star is the more like a local, and then A star is a global. And then how much you know about the environment, and then what is the best way to respond to the some evolving situation. And then overall, try to see whether we can use some quantum for this problem, right? So I don't know, we don't have time to go detail, but anyway, I want to conclude my talk and our talk, especially how do you build a trustworthy quantum robotics is our talk. Especially I try to bring that AI and quantum can work together. And then we can use some digital twin concept in any domain. It can be a robotics, it can be something else, but especially it's very good for the reasoning and simulation, optimization, understand about some of the situation, right? So resilient autonomous is possible based on the combine of this concept. Unknown is can you do the trustworthy optimization? We have several different measurement of the optimization part. We're able to measure about the trust in different way. Then we try to converting about some dynamic trust into the global coordination for the multi-agent performance side. And other one that computing, right? So we said that we're going to use the pipeline approach based on quantum versus AI, the quantum ready environment framework. So we can build some scalable solution for the hybrid QPU versus CPU or GPU, and try to make it some of the quantum native solver is the kind of what we are projecting, and then we want to build up such framework for our research. And from the robotics side, we do the simulation, we do the real-time robot. Collaboration is happening, but really want to deploy this real robot, see how the communication can be done and decision can be intelligently, and then how do you handle about the unexpected situation, unknown situation, adapt to some requirement, right, through some feedback channel. So real-time resilience is the nearly hard problem, but we want to nearly solve this problem. So that is the end of my talk. And if you have any question, please ask me. Look, you want to take over?
Yes.
Hi, Dr. Lee.
Yeah,
I
Tom.
can take. This was great. I really appreciate everyone. Oh, Tom, do you have a question?
I did, yeah. I was actually just curious what your thoughts are on the scalability of this. Obviously right now, even with large language models, they're struggling to get more data centers and GPUs, memory, everything they can get their hands on. And especially with robotics, I imagine that will need even more than what do you think a time frame would be?
So I think, yeah, this is a very important problem, and then it's hard problem. For
Right.
example, we tried building real-time response to the surgery robot. We build a surgery robot, and we have an AI, which is all over the cloud, and we have a real, the situation in the real world situation, like it can be a HoloLens, and then it can be a VR devices, it can be a robot side. But the major problem was the communication. It's, for example, if you go for the request to respond, usually takes about 1 second round trip, right? So from that angle, we cannot just ask anytime what's going on through this communication, typical communication. So what we do is that we are building shared knowledge, not based on the communication, what to do, and then this is what I do, what should be the next one. We are not asking that kind of thing, but we have a shared knowledge between the AI, which is the cloud-based one, and then it's a real robot, it's a real the physics environment. And shared knowledge means we are sharing of some activity in terms of the grid space. Like every activity we can represent in terms of X, Y, Z. And we said that this position is continuous changing. And we're able to calibrate this activity in the real robot. We also understand about the activity from the AI robot, but we can build some shared knowledge through here. And then decision should be done intelligent way, right? That's because of that we use the neurosymbolic AI, which is the knowledge graph together with the deep learning can work together to make it some planning and replanning, and then handling of the situation. We have to change some direction quickly. But I think the physical robot, they don't have much intelligence. So we have to give some good feedback, but the feedback is not based on the typical communication. Feedback based on the sequence of the position in the XYZ. From that way, we don't have much delay. So we can do the real time.
Great, thank you.
Yeah, I think if you think about every activity, either navigation versus finding object or handling of the object, we're able to represent that as a sequence of the XYZ, which is geocoding kind of technique concept. So if you think about any robot arm, we have a 6 degree of the freedom. Each point have XYZ, and movement can be think from the 6 different point coordination. But we able to reasoning, and if you want to do the graphing of the cup, or put in the refrigerator, open the door, everything can be represented as a sequence of the XYZ. But we are not sharing. We are sharing continuously, so we know that we don't have to tell them from the beginning, right? So we building up the shared knowledge from the 3D representation. So that's what we are handling. And right now we're gonna build some robot to take care of the elderly. And for example, we can bring them to the restroom. We want to feeding them, and then we want to clean up, and then we want to take care of them, right? So how do you handling about this task? Sequence of tasks is important. Another thing is we have to use some hand or finger to handling of that. That means that we have to nearly think about some geometric reasoning, so spatial reasoning and temporal reasoning and overall thing. How do you model about some cooking? For example, cutting and washing, and what sequence of action I have to do, and what's the position of your finger look like that. So it's a hard problem, but I think it can be a pretty good way to understand some activity. Think previously, robotics research people using imitation learning to show that how the cooking can be done based on the video data. Sequence of the activity can be shown in the frame to frame, and then robot is learning based on the looking. But takes a long time because the watching video, right, is just not easy. But can you teach them in more intuitive way and more easy way, efficient way? Means can I teach them based on the movement in terms of XYZ sequence? So that's our hypothesis, and we try to prove that this is possible. We handle that based on the basic thing, we can do that. Now we're going to go more complex activity. But the main tool we are using is the transformer, and then we also use the GNN encoder using LLM. So that means this can generate some embedding for the transformer learning about some sequence and then try to producing something new based on some instruction coming. I can generate some new sequence in terms of task, in terms of the position. But still, my point is this is some of the known situation, right? But if it's an unknown situation, from that angle, I think we need quantum computing.
Thank you, Dr. Lee. There's another question in chat, and I might take this one. It's what would need to change in current architectures before current quantum methods could be integrated in systems like KG Transformer? And so with that, NVIDIA has something called CUDA-Q that they've just rolled out, where they're trying to increase the ability for GPUs and QPUs and CPUs to talk together. Yesterday, Dr. Mukesh talked about the high-performance computing integrations they're trying to do. And so I think a lot of the architecture that needs built is in this interoperability domain. For the class computer to talk to the quantum computer, to talk to the high performance, the GPU, the CPU, those kinds of things are what's really needed. Most of us, since we've started machine learning here in the audience, we've always had TensorFlow or PyTorch. But it wasn't that long ago that people were manually coding their backpropagation and things like that. And so I think it's kind of the same thing, where we're working towards a stage where that communication between the CPU and GPU and QPU is still being developed. Yeah. Dr. Lee, thank you so much for talking to us today.
Thank you so much for inviting me.
Yes, no, it was great. I greatly appreciate it, and I think everyone here does. And thank you for your time.
Okay, thank you, everybody. Bye.
Bye.